presenting our project, Predictive Modeling of Amazon Product Ratings. In this project, we explored how to accurately recommend products to users by comparing three distinct approaches: a baseline model, a latent factor model, and the neural collaborative filtering, NCF. Let's start by defining exactly what we set out to do. Our primary task is rating prediction. We take a user and an item as our input, and our goal is to predict the specific star rating from 1 to 5 that the user would give that item. To measure our success, we are using mean squared error, MSE. We chose MSE because it penalizes large errors more heavily than small ones, which is crucial in recommendation systems. Predicting a 1-star when the user would give a 5-star is much worse than predicting a 4-star. We applied 3 models to this task. A item average rating baseline as a sanity check, a latent factor model to capture user-item interactions, neural collaborative filtering NCF to utilize deep learning. We train all 3 predictions for 20 rounds, and after every round, we check their test MSE. For the latent factor program, we use validation MSE to make sure we save its best version before overfitting. Finally, we put all the test MSE on a single line chart to compare the model's performance. For our data management, we split 64% of the dataset into a training set, 16% into a validation set to tune regularization parameters, and 20% into the final test set. A validation set is used to monitor performance during training and select the best model hyperparameters. The model that achieves the lowest validation MSE is chosen as the final model, ensuring its performance generalizes well beyond the training data. For the latent factor model, regularization is applied to the model parameters. This penalty term discourages over-complex models and prevents overfitting to the training data, thereby improving the generalizability and validity of predictions on unseen data. We utilized the Amazon Reviews 2023 dataset collected by the Julian's Lab. Specifically, we focused on 3 distinct categories: digital music, software, and video games. For each category, we downloaded both the user review dataset and item meta dataset. The former served as the primary source for building our recommender systems, while the latter was only for extracting the average rating of each item, which served as a reference for our baseline model method. We chose these specific categories to analyze different types of consumer behaviors, comparing passive consumptions like music versus active usage like software and games. From the raw dataset, we extracted the reviews, which include rating and text, and item metadata, which includes average ratings. However, the dataset is massive, so we applied time filtering. We only kept the most recent 5 years of data from September 2018 to September 2023 to ensure our model reflects current consumers' trends rather than outdated preferences. After selecting our columns such as rating, title, text, item ID, and user ID, we shuffled the data to ensure reproducibility before splitting it. Here's a visual overview of our pre-processing pipeline. It wasn't as simple as just downloading the file. We faced significant challenges with data volume. Initially, we tried loading 8 categories, but this exceeded the 13 GB RAM limit of Google Colab and caused crashes. We had to scale down to the 3 categories mentioned earlier and implement chunked reading of 100,000 to ensure the peak memory usage remains low and manageable. Once the data was loaded, we applied our time filtering, consolidated the columns, and performed the shuffle and split. This clean pipeline ensures that our models were trained on high quality, relevant data. This is our code. Here's our code, and as you can see, we tested time period of 1, 3, and 5 years, and decided to use the 5 years time period. And here we are doing the shuffling and splitting data. This is the shuffling, and this is the splitting data part. In this picture, we're doing the column selection and consolidation. So we're picking these columns and these columns. Okay. So before building the models, we analyze the data to understand the underlying distributions. Observation 1 is the classic J-shaped distribution. As you can see in the chart, the vast majority of ratings are 5 stars, with very few ratings in the 2, 3, or 4 stage range. This indicates a strong positivity bias, showing that people generally only bother to review things they love or are easily satisfied. Observation 2 relates to the volume of reviews over time. We notice a distinct peak in the number of reviews between 2019 and 2020. This aligns with the global COVID-19 pandemic. During this period, consumers are staying home, buying digital goods, software, games, music, and had more free time to write reviews. Observation 3 is about the categories themselves. We found that the data set is heavily dominated by video games. Gamers appear to be active consumers. They engage with the product and review it frequently. In contrast, music listeners are more passive. Because the training data is skewed toward video games, we assume early on that our model would likely be much better at recommending games than music, simply because it has more examples of gaming interactions. Now let's move into the core mathematics of our project. We structured our modeling phase around a consistent mathematical formulation. For all models, the inputs are the user ID, item ID. The output is the predicted rating between 1 and 5. We define our optimization problem as minimizing the mean squared error between the actual rating and our prediction. Specifically for the latent model, we are using the more complex inner product version for the prediction formula. And then we run the bottom optimization problem, which consists of the error term and the regularizer term. The system's job is to find the parameters, the alphas, betas, and gammas, that minimize the overall cost. The cost is the squared difference between our model's predicted rating and the actual historical rating. In simple terms, we are minimizing the error. Finally, the large bracketed term on the right is the regularizer that prevents overfitting. This is a penalty we apply to keep the parameters small and simple, ensuring the model doesn't just memorize the training data, but can generalize effectively to recommend items you've never seen before.
Okay, moving on to the trade-offs of the models. First, the baseline model. The advantage is it is highly efficient and is essentially an instant calculation. And its disadvantage is that it has zero personalization. If you hate a popular game, the baseline doesn't know that, it just predicts an average. Second of all, the Denton vector model. Its advantage is that it introduces personalization through user and item embeddings. It is also interpretable, and we can also look at a bias turn to see if a user is generally grumpy or if any item is universally popular. And its disadvantage is that it assumes a linear relation, which is a dot product between users and items, which might miss the complex pattern. And the third is the neural collaborative routing NCF models. Its advantage is that it captures nonlinear interaction using deep neural layers. It is highly flexible, and its disadvantage is that it is computationally expensive and it is prone to overfitting if not carefully regulated. And I want to highlight a few specific engineering challenges that we solved during the implementation. And the first is the unit time space issue. The dataset stored time as an integer, but pandas converted it to data times object. When we try to convert it back to an integer for filtering, it including milliseconds, creating massive numbers that broke our 2018 filter logic. So we solved this by abandoning Unix conservation and using negative data time comparisons. And the second is the metadata cold start. We found that item in a review data set that did not exist in the metadata set, which means we have no average rating for them. We handle this by implementing a fallback logic, which is if the metadata is missing, we default the global average rating. Let's look at the cog logic. For the baseline model, we create a map linking item to their average rating. The logic is simple. If the item existing in the map, use its average. If it not insists of return the true, means it's cold start item, we append the global average. This acts as our safety net. Uh, about the lantern factor model, we use the alternating less squares. The key line here is the calculation of R prime. We calculate the residual rating. This is the part of the rating not explained by the global average order user item biases. We then solve a system of linear equation, AX equal B. And you can see the non-linear algebra solve the A plus lambda del B vector. So here is the lambda is our regularization term, which prevent the model from overfitting by penalizing large weight, ensuring the learn factor generalize well to the new data. And finally is the neural collaborating filter models. We utilize PyTorch for this. And first, we create embeddings for user and items. These represent the lantern factors in the vector space. Instead of a dot product, we concatenate these embeddings, such as Torcat, and pass them through the series of fully connected layers. These architectures allow the model to learn complex, nonlinear relationship between a user and an item that a simple dot product would miss. And here is our result. The blue line represents the global average baseline model. The orange line represents the lantern factor model. You can see it very stable, and it covers quickly and stay flat at an MSE of roughly 2.26. The green line is the neural network. At approach 5, and CF achieved its lowest MSE of the entire project, 2.1556, which beating the lantern factor model. But however, look at what happens after approach 5. The arrow spikes dramatically to the 2.66. This is a classic example of overfitting. The model began to memorizing the training data noises rather than learning the general patterns. Moving on to related work, we want to highlight the Blair paper, primarily because it is the source of the Amazon Review 2023 dataset that we use for this project. So the Blair introduced the dataset to benchmark complex product search as shown here. Their approach merged LLM like Robert with collaborating filtering to understand review text for semantic retrieval. While they focus on the textual content, we utilize this same high-quality data set to focus on the rating prediction. This comparison helps us contextualize our results. We are applying a different lens. rating analysts to the same modern data ecosystem. We categorize our approach against the field. The first is the trivial baselines. This is the simplest approach which makes the non-personalized prediction based only on item average rating, things like the average rating. This is our starting point, proving that any actual model must do better than this. The second is the linear CF, like our lantern factor, decompose all of the user and items data into the lantern factor to capture simple linear relationship. And the third is the decollaborating filter, which use neural network to find nonlinear and complex interaction that linear model can see. And the next is the sequential CF, like birds for recreation. Use your purchasing or viewing history as a chronological story. It focuses on the order and the sequence of users' interactions over time. It answers the question like, what is the user mostly likely to do next? If it's best for the short term, immediate, and content dependent recommendations. And the last is the content argument approach, like Blair. Take enriched context, such as text descriptions, image, product categories, alongside historical ratings to create highly contextual recommendations. To conclude, our finding align with the broader academic consensus, especially like papered in 2017. And the first is the nonlinear model successfully capture complex interaction better than the linear metric factorization LCFM as we saw, and CPU has the lowest MSE at approach 5. However, the NCF is volatile, it requires strict regularization, and most importantly, early stopping. If we had stopped training at approach 5, we could have had perfect model. And the long-term factor is the safest choice. It is robust, hard to break, and requires less training even if peak accuracy is slightly lower. If we were to deploy system for Amazon, we would like to use the long-term factor model for its stability and or an ensemble of NCF with strict early stopping. So this is our project. Thank you for your time.